Design and analysis of single phase inverter by using Matlab. We have to design this inverter in Matlab and we have to execute Matlab next in Matlab this inverter, and then we will get the sinusoidal output or not. We have to check the sinusoidal output. Okay, so by designing this inverter in Matlab. Single phase full bridge inverter with the PWM operation. Okay, so in previous lecture, I was explained how this triggering pulse are generated by using sinusoidal pulse width modulation. We want this concept go that previous lecture in my lecture. Okay, design analysis of single phase full bridge inverter. Here, this is the circuit diagram of full bridge inverter. Okay, see here, IGBT or MOSFET. This is a device is called IGBT. Okay. IGBT integrated bipolar junction transistor, IGBT, or MOSFET. Okay. IGBT or MOSFETs are used for design of inverter. Okay, because of these devices are having switching loss are less. Okay, very less switching losses. IGBT MOSFET is having very less switching losses. Okay, switching losses are less. Switching losses are less. That's why this IGBT or MOSFETs are generally used for design of inverter. Thyristors are not used because of there is a latching device to turn on the device is very required. Another commutation circuit in thyristors. But here for IGBT MOSFET, commutation circuit is not required to turn off the devices. Okay. So by giving the triggering pulses to the devices, we have to control the signal. That means we have to control the output voltage across the device. Okay. These are high switching devices. IGBT MOSFETs are high switching frequency devices. It is suitable for high switching operations. High frequency devices, high switching frequency devices. But thyristor is not high frequency device. So it required to turn off the device thyristor. So require another commutation circuit. Extra commutation circuit is required to turn off the device. But here not required. Just IDBG MOSFET not required commutation circuit. Automatically turned off when the signal is off. Okay. So this is called IGBT. 4 devices are used. Okay, IGBT T1 and T2 and IGBT 3.1, T3 and IGBT T4. So like this fashion, these all devices are connected. Okay. So here this is called load. So in this operation, single phase full bridge PWM operation, unipolar. This is called unipolar operation. Okay, unipolar operation. In this unipolar operation, so we will get gate pulses 0 and VD. Okay, so 0 and VD. Otherwise 0 or minus VD we will get here 0 and VD concept. Okay, across the load by giving the triggering pulses to the G1 and G3 like this, we will get this type of output voltage. This is called fundamental our. This is called our fundamental output voltage. Okay, fundamental signal, fundamental voltage, sinusoidal voltage. Okay, this output voltage of this frequency of this. Okay, this fundamental output frequency same as our reference frequency. For example, this is called reference frequency. This is called output frequency. So output frequency is same as our reference frequency. Okay, and this output voltage of this inverter can be controlled by controlling the width of the pulses. Okay, so this width of the pulses. Okay, with the width of the gating pulses, by controlling the width of the gate pulse, the output voltage can be controlled. So that means indirectly by controlling the modulation index. By using the modulation index, so we have to control the output voltage of the inverter. So in this design of inverter, so we need This is called one voltage measurement, voltage source, VDC. Okay. So different type of components are required for design of inverter in MATLAB. Okay. So that is called first VDC, and then this is called MOSFET, and next load, for example, resistive load. Okay. And so triggering pulses are required. To give the triggering pulses to this IGBT and MOSFET. So that's called pulse generator is also required. Okay. Pulse generator. Pulse generator is required, and pulse generator is required. And also to generate this sine waveform. Okay. This is also required, sine generator. Okay. Sine generator one component, and also this is also repeating waveform is also required. This triangular waveform. Okay. This is also one component is required in MATLAB. Okay. And then to analyze this, so to understand the voltage across this load, okay, it is channel or not. So we need one scope. Okay, these are the different types of components are required. Okay, and the components are required in this. These are the different type of components. First one is MOSFET. Okay, MOSFET is a switching frequency device. That's why. So in this segment for design of this inverter, this would like to concentrating on MOSFET. Okay, so then sine wave. Okay, this is called sine wave. A reference signal. Our reference signal is called sine wave. So these components we will take from the library of MATLAB. And then next logical operator. This is called logical operator. Logical operator means that may be and or not inside of these different types of logical operators are and or not different types of operators. Okay, logical operators means you are required not a logical operator. So and then next repeating sequence. Repeating sequence here the repeating sequence means this is called a triangular waveform reference signal. Okay, carrier signal is called repeating waveform. So that can be generated by using the repeating sequence by taking the repeating sequence in MATLAB. So we'll generate that's called triangular waveform. And the next DC voltage source that is called here the DC voltage is required. That is called DC voltage source. By entering the DC voltage source in the MATLAB library, so we'll get this component, and also to measure the voltage across the load. Okay, so we need one voltage measurement that is called just like a voltmeter. We have to connect one voltmeter, this voltmeter, okay, in parallel to the load, and then we will get the voltage across the load. And then current measurement, if you want to find the current flowing through the load, the current measurement is required, then current measurement. And this is called a relational operator. Relational operator means just like a comparator. So compare the signals, two input signals, the sine signal and this triangular signal. This compare the two signals, and then so we will generate two different types of signals. I mean triggering pulses. Okay, so like this we have to give the triggering pulses to the thyristors. Okay, so this type of triggering pulses can be generated by using comparing the two signals. That's why. So we need a relational operator in MATLAB, and this called go to and from. These two are required for connect the circuit without physical connections. Okay, physical connections is not required. So directly by using this physical connections is not required by okay, and by writing this labels. Okay, so inside of this, so we can easily directly connect it. Okay, without using physical wires. And then this is scope. Scope is required to analyze the waveform. I mean to get the waveform across the load. So one component is required that is called scope. And also the series bands, series RLC bands. Okay, in series RLC bands, if you want only resistor, there are type of element is called only resistor. That is called only resistor. That is only load. There, select only resistor, then you will get R. If you want to row both RL, take RL branch, then you will get. Okay, by right clicking this series RLC band. So these are the different type of components are required to to design of inverter. Open MATLAB. Once it is open, so the icons are shows like this. Okay, icons are visible like this. So on the icons, press Simulink. Okay, after pressing the Simulink, the new window appear like this. This new window, okay. So blank model or create model, press this create model, and then new worksheet display like this. Okay, this is called our worksheet. In this worksheet, we have to require we have to design this all components. We have to design this inverter in this worksheet. So in this worksheet, to get the elements from the library, so your library browser is there. So press library browser, and then this library. So these are the different type of components. Okay, from this library components, by entering here, then we will get the components. Open library browser like this. So after opening the library, search here for the required components. Okay, search here for the required components. For example, enter here MOSFET. Okay, in this library, enter MOSFET, and then after entering the MOSFET is open like this. And this MOSFET press Ctrl I, automatically move into component worksheet. Okay, so after this, so different type of components are required. So after this, for example, voltage source, DC voltage source. So enter DC voltage source, and so it is display like this, and then add into worksheet model by pressing the Ctrl I. Otherwise, by right clicking the icon, then they will get these components. These are the different type of components like this. So we have to add these all components, series RLC bands. Okay, and the next element is called relational operational. So to want to relational operation, search and then press Ctrl I, and then this will be automatically added into the worksheet. And the next repeating search for repeating sequence. Repeating sequence, so that is called a triangular signal, just like a triangular signal. And then after that, search for logical operator. So the logical operator is called NAT, or and a logical operator is called just like a comparator. Okay, so take from library, so logical operator. Okay, and also sine wave is also one of the components required. Sine wave. Okay, sine wave. Select the component sine wave. Okay, and then mm, after sine wave, uh, scope. Enter scope, and then we'll get scope, and select the scope element and place in worksheet. After that, go to enter go to, then you will get so that components. So go to is display like this. Okay, so go to display like this, and then from also select the from Simulink library. So like this. So like this, all components select the all components from the library. Okay, as the current measurement in library, press current, enter current measurement, and select that item, that component, and set the last one power guide. So this power guide is used required to run the all icons. So continuous power guide. Then after that, close that library window, and now arrange the all components properly. Continuous current measurement and voltage measurement, and from and go to, like this, all components arranged properly. Okay, so next sine wave and logical operator, and repeating sequence, and the relational operator, series RLC branch. Okay, and next DC voltage source, and then MOSFET. So like this, all components, and the press. Okay, select the all components, and here 4 components are required. 4 MOSFETs are required. Select press right click and copy these items. Okay, so now start arrange the all components. Okay, uh, according to our circuit diagram. So MOSFET and MOSFET and MOSFET 1 and MOSFET 4 MOSFETs are required. Okay, MOSFET and MOSFET 2 and MOSFET 3. So like this, 4 components are required, and connect this MOSFET drain. Okay, and drains your source, drain to source, and then your source to source, connect source to source here. And then voltage, one source is required, that is called DC voltage source. So we have to give the power supply at this source this way. Okay, so one side is connected like this, and the second side is like connected like this, and they make the So supply voltage is let us 400 volts supply. So apply 400 volts, and then after that take the series RLC band. So in this series RLC band, we need a filters, LC filter. Okay, that's why this make into 3 copies. This make 3 copies for a series RLC band. So one is called load, one is called L, one is called capacitor. That is called LC filter. So one is required for load, one is required for inductor, one is for double click on this and select this component, just like L. That means LC filter. Okay. So press OK, apply OK, and then that is called connected in series with the load. And then next another component that is called C, capacitor C, that is called. So LC filter is required as capacitor and L inductor. Other than here, select double click on this and only select R. So our load is called resistive load. Okay, and then apply OK, and then OK, press OK. Then close it. So why means so we need filters output. So then continue connecting the other components. So like this. Okay, this inductor in series with the load and the capacitor in parallel to the load. So this is called load resistor. And one current measurement. Okay, to measure the current flowing through the resistor, we need a current 1 ammeter, just like that is called current measurement. And this connect like this, and secondary side of load connect like this. That means capacitor, the load is connected across the parallel to the capacitor. So this way we have to connect. Then connect the second side of the load to the capacitor like this. Okay. And then so we want to measure the voltage across the load. 1 voltmeter is required. That is called voltage measurement. Connect to voltage measurement and parallel to the resistive load. So this way. Okay. So then scope. If you want to measure the waveforms, if you want to know the waveforms across the load, connect scope like this. Okay. Then coming to the inductor design. So here this is called our inductor, and this is called input voltage VDC, and output the inductor is called V output. The voltage at input filter, that is called inductor LC filter here. So this is our input voltage to the filter. This is our input voltage into the filter. Okay, this is our inductor connected in series with the load, and this is called maximum value of ripple current. IA maximum, delta I maximum is called maximum value of ripple current, and delta I minimum is called minimum value of ripple current, and then delta IPP is called peak to peak ripple current, and this is called time period TS, total time period TS. Okay, one complete cycle is called time period TS, and the D is called a duty cycle. Okay, and then the voltage across the inductor is called V is equal to L into di by dt. Then VDC minus V output is equal to L into DIPP by DTCS. Okay, then delta IPP is equal to DTS into VDC minus V output by LI. This is the output ripple current, the peak to peak ripple current equation. And then here, this duty cycle at this is the equation now for a duty cycle at any time. D called duty cycle for any time at any time. D of omega t is equal to MA into sine of omega t. Here MA is called modulation index. Modulation index, and then output voltage is called V naught is equal to VDC into D. This D is called duty cycle. And then delta IPP is equal to MA into sine omega t, TS into VDC minus V, VDC into MA into sine omega t. Substitute this D in this equation. Okay, so we'll get like this. Okay, by Li. So after that, delta IPP remodify this equation. Delta IPP is equal to MA into sine omega t, TS into VDC. 1 minus MA into sine omega t by Li. So to get the maximum value of ripple, so where means by differentiating this equation, ripple peak to peak ripple current and equate to 0, and you will get sine omega t is equal to 1 by 2 into modulation index. MA is called modulation index. So substitute in this equation, and we will get delta IPP is equal to VDC into TS divided by 4 into Li. Okay, so in this equation, TS is called 1 by F. TS, total time period. That is called switching frequency. VDC divided by 4 into L into I. So delta is, so Li is equal to here. So Li is equal to VDC divided by 4 into switching frequency into delta IPV maximum. So this is the inductor design formula. Inductor design formula. So our VDC is equal to 400 volts. Okay, for a design of a inverter, so our input voltage is called VDC is equal to VDC. This voltage is called 400 volts and output voltage is called 230 volts and output frequency 50 Hz. Output power is called 2 kilowatts and switching frequency is 10 kilohertz. These are our input specifications and the total harmonic distortion is less than 5%. So by using unipolar switching operations, we will get 5% total harmonic distortion. THD is less than 5%. If you are using unipolar, bipolar, so we will get more number of switching. Then its harmonics are more for bipolar. Unipolar, less number of harmonics. So that's why THD must be maintained less than 5% and ripple is called 20%. For this values of specifications, so VD is equal to 400 substitute here and then 4 into switching frequency 10 kilohertz into and ripple current. For example, this is current, let us assume 8.69 is called current and into 0.2. This way we have to design the inductor. Okay, so 4.06 millihenry. Okay, this is for design of inductor. Next, capacitor design. Okay, LC filter. This is called low frequency cutoff frequency. This is called low pass filter. Okay, that is called cutoff frequency. Is called FC is equal to 1 by 2 pi into root LC. The cutoff frequencies must be less than the switching frequency by 10. Then only we will get the proper output across the inverter. Then switching frequency by 10 is equal to 1 by 2 pi into root LC. For this, we have to design the capacitor. We will get the capacitor. C is equal to 10 divided by 2 pi switching frequency whole square into 1 by F L. Then substitute inductor L is equal to 4 millihenry and the switching frequency is called 10 kilohertz. And in this equation, we will get capacitance is equal to C is equal to 6.23 microfarads. Like this, inductor and capacitor are designed in a filter. Okay, for a design of inverter. Then change the inductance to the desired value. Change the inductance to the desired value. That is called inductance. How much? 4.06 millihenry. Na? So 4.06 millihenry. Okay, inductance. So enter here 4.06, and then capacitance is equal to C is equal to 6.23. Okay, so microfarads. Enter 6.23 microfarads for design of filters, and the resistance for a load of, for example, this is the load 100 ohms. Okay, so like this filter is designed. Now we shall connect the blocks into the that generate PWM signals. Okay, PWM signals. Okay, this is called a sinusoidal pulse width modulation, sine wave, and a relational operator. Sine wave and a relational operator. So in this relational operator, select greater than or equal to, instead of less than or equal to, select greater than or equal to. Okay, then okay, then apply. After press okay, then apply, and then it will connect like this. And then next, this is called repeating sequence. Repeating sequence, and then after that, logical operators arrange like this, and take go to also connect go to logical operator, and also this is a logical operator. Take NOT gate instead of AND gate. Take NOT gate, and then okay, press apply, and then connect to the output of relational operators. Okay, from there and go to use to connect the pins without using physical wires. This go to is required to means without the physical wires we have to connect. Okay, arrange like this icons. Go to one, so like this, and then from this from is connected to the MOSFET 1, MOSFET 2, MOSFET 3, MOSFET 4 MOSFETs. No? So directly without using physical wires, we have to connect this different type of MOSFET by using from and go to blocks. So connect the gate signal to the from to gate of MOSFET. Similarly, for MOSFET 2, for MOSFET 1, MOSFET 3 also connect from to from A. That means from A. from to MOSFET 2. Okay. Similarly, MOSFET 1, MOSFET 3 also. Gate. Like this. Connect all components. MOSFET is similarly MOSFET 3. So double click on the sine wave. After that, double click on the sine wave. You have to this the amplitude, for example, amplitude 0.45. Amplitude is called 0.5. That is called modulation index. And the frequency 50 Hz. Change the 2 pi f. That is called radians 2 pi f. 2 pi into 50. So after that, press repeating sequence. So on that, enter the values like this. Tap 0.0005. Okay, 0.0001. Like this, time values. These are the called time values, and then output values are called like enter -1, 1, 1, -1, -1, 1, -1. So enter. Then apply. Then okay. So that okay. So like this, properly named from the go to signals. Give the properly name from go to signals. Here, so write here PWM. So write type here PWM. PWM1, then okay, then apply. Similarly, go to 1, here write PWM2. Okay, then okay, then apply. So after this, from A, so enter here PWM1. Okay, PWM1, then okay, and apply. Similarly, on MOSFET 3 also, PWM1, okay, apply. Similarly, MOSFET 1, PWM2. We have to give the PWM2 for MOSFET 1 and MOSFET 2. Similarly, here also MOSFET 2, PWM2. Like this, MOSFET 3, PWM1 and PWM2. We have to give the signals. And set a scope for reviewing the voltage and current. So like this. Set power guide parameters, that is called continuous. Okay. So press on power guide. Okay. And configure parameters, and that tick mark on continuous. Okay. So our required is continuous, not discrete. Then okay, and apply. So like this, all components are designed. Then after that, press simulate. Okay, and that starting time and this called select this called domain price and set maximum setup size and minimum setup size. Okay, 180 power -7 for maximum step size. Minimum step size is called 180 power -8. So like this, keep everything else as it is and plus apply and okay. Click on okay, and then so change. This is called a runtime. So only 0.1 second, 0.1 second is required. Run the simulation, then press run the simulation. Okay, it might be take a few seconds. After seconds, it will be simulated. Then we'll get this output voltage current waveform like this. Okay, so the voltage, this voltage output voltage amplitude is containing 180 volts only. So if you want to change the voltage, okay, magnitude, now we will change the modulation index. By changing the modulation index, so we'll change the output voltage. So instead of 0.45, change 0.9, then you will get more than output, more 180 volts as per previous one. Comparing the previous one, this output voltage will become very high. So then again run simulator, and then you will get like this, and adjust the click here, then you will get this is the output voltage of approximately 370 volts. Okay. Here one of the important concept that is called to get the output voltage 0, voltage across the load 0. Okay. this voltage across the load 0. Okay. So don't turn on thyristor T1 minus IGBT or MOSFET T1, T4. Okay. So if you turn on this T1 and T4, the source will be short circuit. Okay. The source will be short circuit. So don't turn on these two devices, T1 and T4. T1 and T4 are complementary each other. Similarly, T3 and T2 also don't turn on. Okay, these two must be complementary each other. That means if T1 is on, compulsory T4 must be off. Okay, if T3 is on, compulsory T2 must be off. This is a must be take care of connections and also design. Complementary, these two thyristors are, two IGBT or MOSFETs are complementary each other. Okay, if you want to get the voltage 0, okay, don't turn on this two. Okay, by turning on this and by turning on T1 and T3, you will get voltage across the load is 0. So here voltage is called same. This pole voltage, both same, and Vm minus Vb is equal to 0. So like this, that by based on that concept. So turn on these devices. So don't turn on single pole devices. Okay, here and here. This is about design of inverter.